This is lecture 16, and we're going to continue talking about convergence topics, at least for this lecture and maybe one or two more after this. So we've talked about convergence so far, and there are kind of three major forms of convergence, just as a recap, right? There's convergence almost surely, and the way that I establish that a sequence of xn's converges almost surely to a limit x is that if I look at the probability of the event containing all of my little s's in my sample space, little s in my sample space, where xn of s converges to x of s, just as a sequence of numbers. So I look at all the places in my sample space where this happens. If the probability of this happening is 1, it doesn't have to happen for every little s, but it has to happen for a sufficiently large set such that the probability it happens is 1. We call that convergence almost surely. The second topic is called convergence in probability. And convergence in probability, we look at the limit as n goes to infinity of the probability that one of my random variables, my x of n, is more than epsilon away from my my limit x. And if in the limit the probability that we're more than epsilon away from x is 0, we say that the xn's converge in probability. We write xn converge with a p in probability to x. And for almost surely, write xn arrow a dot s almost surely to x. And the final type of convergence is in distribution, a distributional convergence. And distributional convergence purely means that if I look at the CDF of my x of n's at some value little x, this converges to the CDF of my limit, say CDF of x at little x, and this happens for all possible little x. So convergence and distribution, we write xn arrow with a d for convergence and distribution to x, basically if the CDFs of these things converge. That's the 5-second recap of the last two lectures that we've talked about. So today we're going to talk about some properties of these different kinds of convergence, and we're going to talk about the law of large numbers, or a couple versions of the law of large numbers, and we might get to the statement of the central limit theorem by the end. That's our goal here. So the first thing I want to talk about, we can call it a theorem if we want to be fancy, is the algebraic properties of limits. Limits of convergence, let's say. So let me just say, for sequences of numbers, xn, yn, which are just numbers, we have these rules that say, what do we say? We say xn plus yn. Let's assume that the xn's converge to some x and the yn's converge to some y. Then xn plus yn converges to x plus y. We have, what else do we have? We have xn times yn converges to the product x times y. We have xn over yn converges to the ratio x over y. What else do we have? A xn plus b yn converges to ax plus by. So we have these kind of algebraic properties of limits of numbers. So this is kind of a calc 2 feeling. And so some of these algebraic properties transfer over very nicely to convergence. So what I'm going to say for convergence of random variables is that if we have a sequence of random variables x that converges to some limit, sequence of random variables xn that converge to a limit x, we have another sequence of random variables yn that converge to a limit y. I'm not going to say exactly how they converge yet, but if that's true, then 1, a xn plus b yn converges to ax plus by. And this is for, let's say, constants a and b. So numbers a and b, axn plus byn will converge to a plus by. And 2, let's say xn yn converges to x times y. Of course, differences work also, and ratios work also. And we'll formally prove that. We'll say that in a second, but the products converge, but also the ratios would also converge. And so this is true for convergence almost surely, or convergence in probability. So I've written these arrows without really specifying. This is true if I say it's that the xn's and yns both converge in distribution, or both converge almost surely, or both converge in probability. I can put either as or a p over these arrows, and this is true. However, this is not generally true for convergence and distribution. So unfortunately, convergence and distribution is somehow trickier. I should note, though, that so let me say note here that this theorem gives us quite a bit more than I have even alluded to. We can always treat a constant, a sequence of numbers of CNs, let's say, as a sequence of degenerate random variables, right? So numbers are just some kind of degenerate random variables where all of the probability mass is concentrated on one number. So in some ways, convergence of random variables generalizes the concept of convergence of numbers. And so if I have a sequence of numbers that converges to a limit, and we're thinking of this as convergence as numbers, say in a Calc 2 sense, or an analysis sense, then we can also think of this convergence as an almost sure convergence, thinking these as random variables. So why can I say that? If we're basically thinking of these things as degenerate random variables, you can think about why this is true, but it's not too much of a stretch that if they converge as numbers, they kind of converge as really degenerate functions also. So we could think of, anytime you think of a sequence of numbers converging, you could also correspondingly think of, well, that's also just a sequence of degenerate random variables, and they converge almost surely, and hence they will converge in probability, and hence they will converge to this degenerate random variable in distribution, because almost sure implies convergence in probability, implies convergence in distribution. So what does this have to do with our theorem, right? It says that these algebraic properties are true not only for x's and y's, which are kind of true non-degenerate random variables, but they're true for if one of the x or the y's, or both, for example, are constants, right? So the punchline of this is that if we have a constant sequence a constant sequence that converges to some limit c, and we have some xn's that converge to x either almost surely or in probability, then all of the above properties hold if, say, myyn's are not just a sequence of random variables per se, but a sequence of constants, right? So a xn plus b cn will converge to a xn plus bc, and 2, what did we say the second one is, that cn times xn. So if I have a sequence of constants that converges to a limit and a sequence of random variables x's that converge to a limit, then if I multiply these two sequences, this converges to c times whatever the limit of the random variable is. So the theorem is quite general. Now, you would also say x could be a sequence of constants, in which case you basically get back the calc 2 notions that we know, or the kind of analysis notions that we know of convergence. So this theorem is pretty powerful, and it says that for either sequences of constants or sequences of random variables that converge in probability or converge almost surely, we can do these kind of simple algebra. We can multiply by constants, we can add them, we can multiply them, and the limits just either get multiplied by constants, get added, or multiplied. So everything we want to do is kind of really nice. And what we've left out here is, what about convergence in distribution? Now, convergence in distribution is a little bit of a trickier beast. And there is a theorem. Convergence in distribution, there is a theorem that governs some of the algebraic properties. Not quite as nice, because this is not, all those properties are not true for convergence in distribution. But for distributional convergence, we have what's called Slutsky's theorem. And Slutsky's theorem tries to get a similar kind of feeling for distributional convergence. And so Slutsky's theorem says that if I have a sequence of random variables xn's and they converge in distribution to a limit x, which means that the CDFs of the xn converge to the CDF of x, and theyn's converge in probability to some constant c. So here c is a constant. So theyn's converge in probability to some degenerate random variable. Then we get the nice algebraic properties that we want, which is that, let's say xn plus yn converges in distribution to x plus c. What else do we have? The product xn times yn converges in distribution to x times c. And you could also say, xn over yn converges in distribution to x over c. You could also say that, and we'll formally prove this, but you could also say that for this case, which is that xn over yn converges to x over y. So that's Slutsky's theorem, which tries to get some of these algebraic properties for distributional convergence. If we have an xn and a yn that both, right, so the kicker here is that this thing, the c, the limit of theyn's has to be constant. We can't have theyn's converging to a non-constant distribution. It doesn't, as it happens, work out unless that thing is constant. And this is kind of reminiscent of the relationship we saw before between convergence and distribution and convergence in probability. In fact, we could have easily have written this as the YN's convergent distribution to a constant here, because we know that if the limit is constant, is this kind of degenerate random variable, there isn't a distinction between convergence in probability and convergence in distribution. They're the same thing. Okay, so that's kind of the algebraic properties for convergence and distribution. So basically, if you're working with probability and convergent probability or convergent surely, do whatever algebra you want. Or if you're working with a sequence of constants, do whatever algebra you want. It all works out. If you're working with convergent distribution, you got to be careful. The algebra only works out if one of them has a constant limit. The other one can have a like the x's can converge to some non-constant x. But the other sequence, the y's, have to converge to a constant. And then we can do our algebra we want. But you can't have both of them be non-constant. So unfortunately, life is a little more complicated than we'd like. Another really useful theorem, it's hard to understate how useful this is called the continuous mapping theorem. Continuous mapping theorem. And the continuous mapping theorem says that if we have a function, a real value function, g, and if g is a continuous function, and xn converges to x in any type of convergence, then g of xn converges to g of x. So this is super powerful because as long as you have a continuous function, it doesn't even need to be differentiable, just continuous, we can apply to both sides of a limit for any of the types of convergence we talked about. So that helps us out in a ton of places, and it's a very general theorem. Now the proof of that, it's not so much a proof as a definition, right? So if you were to take an analysis class, which isn't really a prerequisite, but kind of the aside here, or the motivation, is that in a real analysis class, so this is something we don't need to know for an exam. Analysis is not a prerequisite for this course, but probability is basically, and stats is basically analysis. That's all it is. In a real analysis class, you define the kind of big boy definition of a continuous function as a function that preserves limits. So that if we have a sequence of number xn that goes to x, then g of xn goes to g of x. And if this is true for any possible sequence, we say g is a continuous function. That's the definition of what it really means to be a continuous function, is that it's a limit preserving function. So in that light, the continuous mapping theorem needs not so much a proof as just to be reminded of the definition of continuity, which is that by definition, what continuity means is that the limit is preserved. So this is why it works for any type of convergence, because it's basically a basic property of what any type of convergence means, is that it is going to be preserved by a continuous function. And so the continuous mapping theorem says yes, right? This is true for convergence in, almost surely, in probability and distribution. These are just types of convergence, and a continuous function will preserve them because by definition, a continuous function has to. So one of the nice, really quick examples of this, we had said above, way back up when we started talking about algebraic properties, that, for example, like the product converges to the product of the limits. And I said, well, this also works for ratios. Why is that true? Well, it's basically the continuous mapping theorem, right? So let's just look at an example. If yn converges to y, and every time in this lecture, if I write it without specifying what type of convergence, it works for any type of convergence, or I'll specify which types it works. But if we have a sequence that yn that converges, say, almost shortly or in probability to y, and let's say these yns are bigger than 0 and y is bigger than 0. Let's say strictly bigger than, right? So the y's are bigger than 0 and the limit surely then it also has to be positive. That's actually not true. It has to be bigger than or equal to 0. But let's say that both of them are strictly positive. Then the continuous mapping theorem says that, g of, let's say, y is 1 over y is continuous, as long as y is bigger than 0. Hence, g of yn converges to g of y, i.e., 1 over yn converges to 1 over y. And what that means is that if I have another sequence xn's that converge to x, then xn over yn, as long as I can do products of things, I can take the product of the 1 over yns and the xn's, will converge to, of course, the product of the limits. So that's why that ratios of random variables is kind of a special case of the product rule for convergence of random variables, because we have this continuous mapping theorem, and as long as your yns are not 0, you can run your problem through 0, but we're good. Okay. So that is some basic properties. I want to define a term here that you will see, and this is purely a redefinition. And the definition, you wouldn't see this in the probability class, but of course this is a math stats. Let's not forget. This whole section on convergence really could just be in a probability class. We don't have time to teach it in 451, so we put it in 452, which is a very nice place for it. But all this stuff we haven't really talked about estimation so much. We'll get back to it, but we have what's called a consistent estimator. And so back to estimation. We say an estimator, let's call it theta hat n. So it's going to, here this thing is based on n samples, all right? And n could grow. We could talk about the convergence of it as it grows. We say that an estimator theta hat of n samples is consistent for the parameter it's estimating, theta, if theta hat n converges in probability to theta. So you will see sometimes people talking about consistent estimation, and this is consistent for this parameter, or something like that. It's just a rebranding of convergence and probability, but it's the terminology that is used in math stats, which is that an estimator is called consistent, it converges to probability, and probability to the parameter. Notice that this thing here is a constant. We get to Bayesian probability at the end of the class. Maybe we'll have some time for a lecture too. Theta might not be, but for classic frequentist probability, theta is just some constant. And so just FYI, right? So you could also say distributional convergence, but typically it's cited in terms of probabilistic convergence. And all consistency means is convergence and probability. The idea being that I have some PDF for theta hat, and it doesn't have to be normal, but maybe it's something like that. I want to make it kind of non-normal. Let's make it like that. All right, so it's not normal. It doesn't have to be normal, right? And this is my PDF or whatever PMF of theta hat. and this is my truth theta here, right? And as I increase n, if I'm consistent, consistency means that the probability collapses around the truth, right? It means that the probability I'm far from my truth goes to 0, right? What does consistency means? It means that the limit as n goes to infinity of the probability that, say, theta hat is too far from theta goes to 0. So this is basically, the probability is the probability that theta hat is far, whatever far means, for whatever epsilon, from theta. And consistency means this probability goes to 0. And so what should happen is that as I increase n, I still have my true theta somewhere, is that we're hoping that this PDF is collapsing around. I just want to make something look not quite normal. We're hoping it's kind of collapsing around around the truth. So it's tighter, my PDF is tighter around theta. More probability concentrated around theta. And as I keep increasing my n, if I say maybe n goes to infinity, it's going to collapse and collapse and collapse until eventually what I'm going to get, if I really have probabilistic convergence, is I'm going to eventually collapse to a point distribution around or concentrated on theta. One way, so that's definitely one way of thinking about this. Another way of thinking about consistency is that consistency is basically asymptotically unbiased. That's often how people will talk about consistency, as kind of an asymptotic unbiased. There's a technical caveat here that this is only true for regular enough distributions. If you have a very non-regular distribution, then this kind of idea doesn't make sense. But the kind of typical example people have in their mind, right? So if I have s squared, which is my sample variance, right, and it has this formula, something like that, we know all the way back to lecture, whatever, 1 or 2 or something, that this thing is unbiased, right? I don't even know anything about x's. We just know that that thing's unbiased, right? So unbiased. I guess I need to know there's a finite variance. And we could also look at what was maybe sigma hat squared, and this was the MLE for, say, a normal, was we saw that the 1 over n minus 1 got replaced with a 1 over n. And this thing is not unbiased, right? We can just know, because we're replacing 1 over n minus 1 with a 1 over n, that the expected value of sigma hat squared here is something like n minus 1 over n sigma squared, right? So it's not unbiased. And however, the expected value of sigma hat squared, as I increase n over n minus 1, I guess I was calling it capital N here, n over n minus 1 goes to 1, this thing will converge to sigma squared. So asymptotically, the bias of this thing basically goes to 0, because asymptotically the expectation will work. And consistency is kind of a measurement of the asymptotic unbiasedness. If something's consistent, then it's kind of asymptotically unbiased. There is a kind of more formal way of stating this, which is that if the MSE of our estimator goes to 0, then our estimator is consistent. So if the MSE goes to 0, then theta hat is consistent. I'm going to drop the n on theta hat. Just, we know it depends on a certain number of samples when they talk about limits, whatever. So we can write this formally. I mean, that's pretty much it. If the MSE of my estimator, theta hat, as n gets larger, if the not to go to theta, if the MSE goes to 0, then theta hat converges in probability to theta, i.e. theta hat is consistent. Again, we should say it's consistent for something, consistent for the parameter theta. As opposed to consistent for theta squared. Okay. It's supposed to be a theta there. We can prove this. And it's actually not too bad of a proof. It uses one of the inequalities, and it uses Markov's inequality. And so the reason I taught you Markov's inequality, not only to teach you Shebachev's inequality, is because it can be used to prove things like this. So let's just look at the proof of this. Right, so what do I need to do to show consistency? I need to show that the probability, let me just say, showing consistency is the same thing as showing that theta hat converges in probability to theta, which means that the probability that theta hat minus theta is bigger than, if I pick any epsilon, so for any epsilon, the probability that theta hat is more than epsilon away from theta in distance. This thing, as I increase, say capital M was my sample size, this thing should go to 0. The probability I'm more than epsilon away from the truth theta goes to 0 as I get a bigger sample. So Markov's inequality, if you remember, said that, what did Markov's inequality say? It said that the probability that a random variable was bigger than or equal to A was, what did it say, less than or equal to? I believe that. Less than or equal to the expected value of X over A. Right, so that was basically Markov's inequality. And so we can use this here. And if I let X be, well, first of all, let's say that the probability that theta hat, the distance between theta hat and theta is more than epsilon. I can, of course, square both sides of this. So this is the same thing as saying the probability that theta hat minus theta squared is bigger than epsilon squared. And Markov's inequality did have this condition that X was a non-negative random variable. Of course, a squared random variable is non-negative, so let's let that thing be our X. Then by Markov's inequality, this thing should be less than or equal to the expected value, theta hat minus theta squared, over A, here this thing is A, epsilon squared is A, so this thing becomes epsilon squared. So what do we call the top there? That is the MSE of theta hat, right? The MSE of theta hat is the expected squared distance of theta hat to truth. So this is basically the MSE over epsilon squared. And so if my MSE theta hat goes, as I increase my sample size, to 0, then this probability is always positive. And I'm going to, basically, the Squeeze theorem, back from Calc 1, says that I have something that's bounded. I have my 0 line here, and I have some upper bound, which is my MSE over, so this line is like the MSE of theta hat over epsilon squared. If that thing goes to 0, and we know that this probability here is between this MSE and 0, then by the Squeeze theorem, Squeeze theorem says that it must be this probability, which of course is probability theta hat minus theta, and epsilon also must converge in the limit to 0, i.e. theta hat is consistent, or theta hat converges in probability to theta. So that's a cute little proof, and that's a nice little proof using Markov's inequality, which we had done before, just so we can use it in these kind of cases. So let's change gears a little bit. And for most of the rest of this lecture, we're going to talk about what's called the law of large numbers. There's actually a couple different versions of the law of large numbers, and that will lead into a discussion of the central limit theorem. The basic intuition behind the law of large numbers is that if x bar is our typical mean, let's say, this should be a good approximator, or a good approximation of the mean mu, which is the expected value of any of these things, right? Now, you may, in other statistics classes, in intrastats or many other things, you hear the word approximation. It's not a particularly rigorous word when used in those contexts. The way to make this all rigorous is to talk about convergence. So one of the reasons we want to talk about convergence is you can talk rigorously about what it means to be an approximation or a good approximation of something. Nonetheless, the intuition is that, of course, x bar should be a good approximation of the mean, right? We know the expected value of x bar will give us this mean. Every single sample you draw is not going to have a sample mean x bar that is exactly equal to mu. But we expect that maybe for large samples, for large numbers, this will actually be a good approximation. In fact, we saw in certain cases, in many cases, it's the best estimator for a finite sample. And so the way that this is formalized is through the law of large numbers. And there are a couple of versions of it. The simplest and weakest being the weak law of large numbers. Now that's a real mouthful to write down, weak law of large numbers. So it is almost always abbreviated as WLLN, weak law of large numbers. Occasionally see just LLN for law of large numbers. But to be precise, we have to specify exactly what form we're talking about. Now, this is something that people sometimes will call the law of averages. Not to be confused with the law of surprise, but the law of averages, I haven't really heard that term used among kind of serious probabilistic statisticians. The real serious way of talking about it is what's called the law of large numbers. And the weak law of large numbers says basically the above, that xn is going to be a good approximation of the mean of random variables for basically any distribution. And by good approximation, we mean it's going to converge in a nice way. So to state the theorem, we're going to say we have some x, let's say little n's, that are uncorrelated. I'm going to write this. Xn's, let me write what I said. We have some sequence xn's that are uncorrelated. And they all have the same mean. So the expected value of any of these things, we're just going to call that mu. It's the same for all of them. And they all have the same variance. The variance of xm, we'll call that sigma squared, and it's a finite variance. I guess you could specify that the mean is also finite. If the variance is finite, the mean will be finite, though. And these things have to be uncorrelated. They don't have to be necessarily independent. They have to be uncorrelated. If we have this, then if I calculate x bar on, say, capital N of these, all right, so I'll just write this out again, exactly what I mean. I'm going to sum up the first n of capital N of these and divide through by capital N. So a typical sample mean. The weak law of large numbers says that this thing converges in probability to mu. So we call this, quote, weak, a weak law of large numbers, because its convergence in probability, so it's weaker than, say, convergence almost surely. It's kind of a weaker form of convergence, but it also has say, weaker requirements than one might. That's not how you spell requirements. Requirements than one might otherwise. So we're talking about a strong law, and this is weak in compared to that strong law, but it has weaker requirements. All these things need to be is uncorrelated. They don't have to be independent. They just have to be uncorrelated, and they have to have some finite variance. So it has kind of weaker requirements of it, but it then also gives us a weaker form of convergence. Converges in probability. It doesn't necessarily converge. If we just have uncorrelated things, they're not necessarily going to converge almost surely. So this is the weak law of large numbers, and it can be really, really the crux of it is that x bar converges in probability to mu. So that's what you should take away here, is that the weak law of large numbers says that x bar converges in probability to the mean. This is actually within our wheelhouse to prove. And it's not too bad of a proof because we know Shebachev's inequality. I'm gonna prove I'm not gonna prove the fully general version when we just have things that are uncorrelated. Don't think we have quite enough to prove that. Yeah. So let's just talk about I don't want to get into a PhD level proof of the uncorrelated case, but let's just prove a kind of simpler case where my x sub n's are IID and the expected value of each of them is mu. The variance of each of them is sigma squared, which is finite. So this is a little bit of a stronger form than the weak law really requires. You actually only really require uncorrelatedness, but let's just prove it for the IID case. Notice then that we know that the expected value of x bar is, of course, mu, and the variance of x bar is sigma squared over n. And by Shebachev's inequality, the Shebachev inequality had several forms. One of the useful form we're going to use here is that, and we wrote this out in different forms when we talked about Shebachev to start with, is that if I look at the probability that x minus mu is bigger than or equal to some epsilon, this is less than or equal to variance of x over epsilon squared. And so this was Shebachev's. So Shebachev's inequality for x bar is that the probability that x bar minus mu is bigger than or equal to epsilon is less than or equal to the variance of x bar over epsilon squared. Of course, the variance of x bar is sigma squared over n. And so Shebachev says that this probability, which is not negative, is less than or equal to sigma squared over n. And of course, this thing, as n increases, will go to 0. Sigma squared is fixed. Epsilon squared is fixed. And as n gets bigger, this whole thing goes to 0. And it will squeeze this probability, because that probability is bounded between 0 and something that goes to 0, by our Squeeze theorem, which is, say, a Calc 1 theorem. We know that this thing also will go to 0. And what does that mean? X bar converges in probability to mu. So that's quite nice. That's it's a real simple proof just using Shebachev's inequality. So Shebachev's inequality basically gives us the weak law of large numbers. We can generalize this a bit. Let's just first do an example, though. So here's an example. Notice we don't need this to be normal. We don't need anything. We just need, some xn's, and let's say maybe the xn's are IID from a Poisson distribution with some parameter lambda. So they're IID, they're independent, they're certainly uncorrelated. The expected value of any of these xn's is lambda. And of course, the variance of any of these xn's is also lambda. It's a Poisson distribution. That's certainly finite. And so what the weak law of large numbers says is that if I look at x bar for these mean of these Poisson, this will converge in probability to lambda, to the mean. And Poisson was an arbitrary choice here. It's true for normal, it's true for beta, true for pick your favorite Bernoulli, pick your favorite distribution. It's true for all of them, as long as you have uncorrelated things that have a finite variance. There are many different versions, so that's the kind of standard weak law of large numbers. We can make this more interesting. Is that we don't, there are various, over the years, people have developed various versions of the weak law of large numbers, taking out things that you don't really technically need. So let's assume that that the variance of each of my x events are not the same. Maybe they have different variances. So the variance could change for my x's. But we have the condition that if I take, say, the average of these variances, this thing is always finite. So for all n, this thing is finite. And we can get a similar, can derive, that's supposed to derive a similar rule to the weak law of large numbers, because by Shebachev's, if I can spell Shebachev's name, inequality, we can again say that the probability that x bar minus mu is bigger than or equal to epsilon is less than or equal to the variance of x bar over epsilon squared. But now we have that, you know, before when the variances are all equal, the variance of x bar was just the variance of was sigma squared over n. Now this is the variance of x bar is going to be 1 over n squared times the sum of these things, right? And so now you see where my condition here is coming from, that that thing better be finite. And hence this thing is equal to, let's say it's 1 over n, and then on top we'll put one of the n's, and then we'll say it's 1 over n times that thing, right? So I've just pulled one of my 1 over n's out front. This thing is less than infinity, and this epsilon squared is constant, and so this whole thing will go to 0 because we just kind of 1 over n times something that's finite, and that thing will go to 0, and hence xn converges in probability to mu. So this is not the kind of standard weak law of large numbers, but you can relax it in various ways, and people have over the years. But the standard weak law of large numbers is basically this thing here. So that's kind of what I would try and memorize, which is that xn converges in probability to the mean. Now, as long as I have uncorrelated things with the same mean and, let's say, finite variances. You can also use this, so it looks like the weak law of large numbers. Again, you can play various games with it and get kind of other rules from it. It looks like the weak law of large numbers only talks about means, but there are other things out there, for example, sample variances that kind of behave like means. So consider s squared, right? This is s squared. Now this kind of looks like a mean, right? It's 1 over something like 1 over n times the sum of some things. So it's kind of like a mean. And in fact, again, if, you know, my x n's are independent, and and they all have the same mean, and they all have the same variance, we can show, in a similar way to how we showed the weak law of large numbers, we can show that this sample variance, right, which depends on n, I'm not going to write that, but depends on n, we can show that this thing converges in probability to sigma squared, right? So, and it's basically, we can just kind of recapitulate our proof of the weak law of large numbers, and everything goes through. And the reason it works is because it's kind of like a mean. So the weak law of large numbers is not only talking about means, it's kind of talking about sums of things, kind of properly normalized, kind of mean-like things. You can often, not always, but often derive similar rules, right? So we can show this. We can show that, you know, this is why I don't want to just teach the weak law of large numbers, because you wouldn't be able to then be able to reason about, say, the sample variance and say, well, it's not a mean. But it's close enough that you can do a similar kind of game to get what its limiting distribution, or what it, you know, converges to show it's, what do we call this? This says that s squared is consistent for sigma squared, right? That's exactly what that's showing, which is interesting. So again, we can use Shebachev inequality, right? What does Shebachev's inequality say? It says that the probability that s squared minus its mean, right? So Shebachev's inequality generally says that the probability that some random variable y minus its mean is greater than or equal to some epsilons less than or equal to the variance of that thing over epsilon squared, right? That's a version of Shebachev's. Maybe, yeah. And so if I apply this to s squared, what's the mean of s squared? We know it's sigma squared, right? That's because the expected value of s squared, we said this is sigma squared. And the probability of that is greater than or equal to epsilon. We know by Shebachev's inequality that you're gonna use Shebachev's a lot in the homework, so you get used to using it. This is less than equals the variance of this thing. Well, I don't know, right? So let's say it's the variance of s squared divided by epsilon squared. So maybe I should put a question mark. Can we show this? If I can show that the variance of s squared goes to 0 as n gets large, then we have that s squared is consistent for convergence and probability to sigma squared. So an example here would be if so this is going to depend on exactly the underlying distribution. If I have my x's are IIDs from, let's say, a normal mu sigma squared distribution, then we can show, I think we might have showed this in one of the very early lectures, that the variance of Sn squared, so you can always, the expected value of s squared is always sigma squared, or no matter the distribution. The variance can depend on what the true underlying distribution is. That will change. But for a normal distribution, we can show, and I think we did show this, is that this is 2 sigma to the 4th over n minus 1. And so certainly this thing, as n gets large, goes to 0. And hence, in this situation where we have normally distributed things, s squared is certainly consistent for sigma squared. So that's nice, at least in our normal case. And more generally, as long as you can show that the variance of my s squared for my distribution basically goes to 0 as I get more samples, then we can show that s squared is consistent. Because we know s squared is unbiased. So this actually could be proved by just showing that this is equivalent to saying that MSE goes to 0. So you can use our previous theorem and actually get this directly too. Our add-on here, just to bring in our continuous mapping theorem. Continuous mapping theorem says that the square root function is continuous. So the square root of s squared surely converges to the square root of sigma squared in probability. Let's say if we know that s squared is consistent for sigma squared, then the square root of s squared will be consistent for the square root of sigma squared, i.e. s converges in probability to sigma. So this s is, the sample standard deviation, and sigma would be the population, SD. So you can see how powerful this continuous mapping theorem is. It says, square root is continuous, great. So, so we get convergence. So we could just take the square root of both sides. And this would be true if you want to take the 5th power of this, right? It's also a continuous function, so that would converge. But so under some kind of relatively weak assumptions, certainly true of the normal case, s squared will be a consistent estimator for sigma squared. So that's a good fact to know. Okay, now, so we show this for s squared. What about sigma hat squared, which instead of having 1 over n minus 1, was a 1 over n. So this was the MLE in the normal case. And I think I made a claim earlier that you could show that this thing is consistent for sigma squared. So can I show that this thing is consistent? Let Cn be n over n minus 1. Then Cn converges to 1, right? As a sequence of numbers, that then converges to 1. And so by our algebraic properties, we get that Cn times sigma hat squared converges to 1 times, then let me back up here. Is that what I want? Then since, right, so we know that S squared is consistent for sigma squared, and S squared is equal to, why don't we reverse this? This is going to make the argument easier. Say n minus 1 over n still converges to 1, right? Sigma hat squared is equal to Cn times S squared. And so if S squared is consistent for sigma squared and Cn's converge to 1, then we know by our algebraic properties here that this thing is going to converge to 1 times sigma squared, or sigma squared. And so, and that's convergence probability. And so sigma hat squared is also consistent for sigma squared, right? And that's just using our algebraic properties. So consistent estimators are not unique. Unlike U and BUEs, we can have multiple different estimators that are consistent. And it's believable that if S squared is consistent and we're just kind of slightly changing it from n minus 1 to n, in the limit, that's not going to matter because as n is really large, n minus 1 and n are kind of basically the same thing. So we're not going to get a hugely different limit there. Okay. So that's just kind of playing around with other versions of the weak law of large numbers. There is another thing called the strong law of large numbers. Which is appropriately abbreviated SLLN, for strong law of large numbers. And we're not going to do a proof of this, but I'm just going to give you the statement. This does require that the xn's are IID with from some distribution where they all have the same mean, mu, and they have the same variance, sigma squared, that's finite. If that's true, x bar on n samples converges almost surely to mu. So in the weak law, we actually only need uncorrelatedness of the xn's. If they happen to be independent, we get what's called the strong law, and we actually get almost sure convergence. So it's stronger because it has a stronger condition, that is independence, but it also gives us a stronger form of convergence, that is almost sure convergence. So that's about as much as I'm going to say about that. I'll just say one more thing. So the weak law of large numbers, just contrast the weak and the strong laws, is that basically is that x bar gets close to mu as n increases, but it's possible with non-zero probability that x bar can be arbitrarily far from mu. Now, it has to be that in the limit, the probability that x bar is arbitrarily far from the mean has to go to 0. But for any finite n, there is a potentially non-zero probability that x bar is arbitrarily far from mu. So what do I mean by arbitrarily far, right? If I look at x bar, the distance between x bar and mu, and I say, what's the probability? So if I ask, the probability that x bar is more than some arbitrary epsilon away from the true mean, mu. As we know that the weak law says that in probability this thing goes to 0 in the limit, right? That in the limit this thing is going to hit 0 or approach 0. But if I pick an arbitrary n out here, there may be some non-zero probability that says that x bar could be more than epsilon away. And for any epsilon I choose, it's potentially true that x bar could be more than that epsilon away from mu for some finite n. So it's only kind of in the limit that you could be arbitrarily far away. So that's why it's kind of weaker. It's, as I get bigger and bigger n, the probability is going to go to 0. It's going to be less and less and less likely that I'm arbitrarily far from the mean. But it's nonetheless, it's possible. The strong law of large numbers says that this thing has to hit 0 at some point, some finite point. So x bar can't be arbitrarily far from mu beyond some point. So again, if I look at the probability that x bar is more than some arbitrary epsilon away from mu, the strong law, because it's almost sure convergence, means that at some point here, there is going to be some point where this has to hit 0. You can't just asymptotically approach 0. No, it has to hit 0 beyond some point. And so that's basically the strong law, is that it might depend on the epsilon, but if you give me an arbitrary threshold and say, what's the probability that I'm more than that away? I said, there is a point, if you go further enough out in your sequence, that probability will be 0. Not just asymptotically close to 0, but will be 0. So that's kind of the relationship just between almost sure and convergence and probability, but in the context of weak and strong law. And so the weak law is a little bit weaker, but you need weaker conditions to satisfy it, so it's more generally applicable. But at the end of the day, they're both talking about convergence of the mean, or kind of mean-like things. So in closing, I want to kind of set up the central limit theorem for next time. So here's our example. We saw that my sample variance, actually let's say my sample standard deviation, was consistent for the population standard deviation, sigma. And so if you look at sigma over s, that will be consistent for 1, or that will converge in the probability in 1. And that's just an algebraic property, right? I can multiply each side by 1 over sigma. Our algebraic properties say that's cool. I can definitely do that for actually any of my modes of convergence, because sigma is constant. And let us assume that that if I look at x bar minus mu and I divide through by sigma over root n, let's assume that this converges in distribution to a standard normal. Now, let's call this whole thing, let's say yn. This will be the whole topic of next lecture, but let's assume this thing, if I basically z-score x bar, subtract off its mean, divide through by its standard deviation, let's assume, who knows, maybe it will be, maybe it isn't, but if we just take that on faith for now, that this thing converges to a standard normal, then what can we do? Well, let's basically look at a t statistic, which is a t statistic is basically x bar minus mu over, it replaces, so this is like a z statistic by nu sigma. A t would replace that sigma with an s. So it looks something like that. X minus mu over s over root n. Then this kind of t-ish statistic, although I haven't really said anything's normal, this kind of t statistic, the question is, can you get a distributional limit out of this? Notice here that I can write this as sigma over sigma. Certainly that's 1, so that's okay. I'm going to bring my root n up top. Am I going to do that? We can leave it in the bottom. It doesn't really matter. Say x bar minus mu over, say, 1 over root n. And let's bring my 1 over s out of that thing, right? And I can say this is sigma over s, x bar minus mu over sigma over root n. And we had called this thing yn, and we had said that it converged in distribution to a standard normal. And furthermore, we had started this whole thing by saying that this thing converges in probability to 1 by Slutsky's theorem. If you go back and you look at Slutsky's theorem, says that if I have something that converges in probability to a constant, namely sigma over s, and I have something that converges in distribution, and I take the product, this whole thing should converge in distribution to the product, which is 1 times a standard normal, i.e. a standard normal. So this t is basically, I guess it should be a capital N here, right? It's basically kind of like a t statistic. And if you from an intro stats course, there is this claim that t statistics are like normal distributions, and that they asymptotically, as our n gets really large, they basically become a normal. So that's basically what we're showing here. And you can show that now because we talked about how s is consistent for sigma. And it kind of relied on this fact here about this x bar minus mu over sigma root n, which might look kind of familiar from an intro stats. It relied on this distributional convergence of this thing. And that's going to be the topic of next time's lecture. Is we're going to look at this kind of quantity and when we can get a distributional convergence to a standard normal or something like it. So I think we're kind of at time, so we'll stop here, and we'll have definitely one more, maybe 1.5 or 2 more lectures on convergence, but it will start getting more interesting and bring it back to kind of concepts we're familiar with, like t statistics or normal distributions, and actually rigorously show some of the stuff that you taught, I don't know, high school freshman year in an intro stats course. We're actually going to show it rigorously now, because when you say this is approximated well by a normal distribution, what it means is distributional convergence. So let's stop there because we're at time, and we can pick up here and talk next time about the central limit theorem, which is maybe the most important theorem in all of mathematics.